Hello Year 10, this video is a summary of the organic chemistry topic, which mainly focuses on the uses and processes involved with crude oil. So first of all, we need to discuss what is crude oil. So crude oil is a finite resource, which means that it is non-renewable and can only be used once. It has been formed over millions of years from plankton that was buried in mud, and these large layers of mud on top of the plankton have created high pressures and temperatures in the absence of oxygen, allowing the crude oil to form. Crude oil is a mixture, which means it contains two or more elements or compounds, in this case different compounds, that are not chemically bonded together, and that's the important part. They are not chemically bonded together, and many of these compounds present are different hydrocarbons, which is a group of compounds that contain only hydrogen and carbon atoms. So, as discussed, crude oil mainly contains different hydrocarbons, and most of these are called alkanes. The first part of the alkane name tells you how many carbon atoms there are in each molecule. Alkanes are described as being saturated hydrocarbons, which means that they only contain single carbon-carbon covalent bonds. There are no carbon-carbon double bonds present. And this means that they contain as many hydrogen atoms as possible, and no more can be added. This means that their general formula for alkanes is CnH2n plus 2, which means that for every one carbon there is two hydrogens plus an extra 2 per molecule. Pause the video now and try to draw the molecule of octane. This molecule will have 8 carbons. So, here is a table that summarises some alkanes that we need to know about. So, methane contains 1 carbon, and that can be seen in its formula and in its displayed formula, which has 1 carbon surrounded by 4 hydrogens. We have ethane, which has 2 carbons, propane, which has 3 carbons, butane, which has 4, and then I've also put octane, which has 8 carbons down here, so that you can see if you manage to draw it correctly. So you should have 8 carbons in a straight chain, all joined by a single bond. There should then be 2 hydrogens coming off each carbon, plus an extra 2, 1 at each end. Okay, so then we have to learn about the properties of hydrocarbons. So as the size of the molecule increases, so there's more and more carbon atoms, the boiling point increases, and the boiling point is the temperature at which the liquid boils or the gas condenses. The volatility also decreases, and the volatility is the tendency to turn into a gas. So if we have a very small hydrocarbon, this is much more likely to turn into a gas than a very large hydrocarbon. So we also have, as the size of the molecule increases, the viscosity increases, and the viscosity is how easily the substance flows. So if I have a small hydrocarbon, such as, I'm trying to think of one that isn't a gas, octane, it will pour very easily. Whereas if we've got one of these very large hydrocarbons, this will not pour nowhere near as easily and will be like a thick syrup. And then the flammability of the molecule decreases as it gets larger, and this describes how easily it burns, which means that our smaller hydrocarbons are much better as fuels because they burn more easily. Here is a picture showing how we can separate crude oil, because remember it is a mixture and we might want to separate it into different parts. So crude oil can be separated on a small scale using this distillation apparatus. This can be done in a normal laboratory with obviously some safety considerations. So we heat the crude oil until it all evaporates into a gas. The different fractions vaporise, so go into a gas, at different ranges of temperatures. So we can collect these different fractions by cooling and condensing the vapours into different boiling tubes, and that's what this cold water is doing. That's helping to lower the temperature to enable us to collect the different fractions as liquids rather than as vapours. this is how we would separate crude oil on a much larger scale. It is called fractional distillation. The diagram shows a fractional distillation column where the oil is heated and pumped into the bottom of the column here as a hot vapour. The temperature decreases as you go up the column, so you can see it's around 350 degrees here and only 50 degrees at the top. So as the gases move up the column, and they will condense when they reach the temperature of their boiling point. So for example, kerosene will get to around here and condense from a gas to a liquid, so it can then be pumped off here. So the different fractions are collected as liquids in a continuous process, so we just continue to keep pumping the vaporised oil in and pumping the different fractions out the other side. The smallest hydrocarbons have a lower boiling point, so are piped out at the top of the column, whereas at the bottom of the column we find the largest and long hydrocarbons that have the highest boiling point, and these are often found as thick liquids or solids at room temperature. So as you can see in this diagram, it describes something called a residue, which is a sticky mixture of long chain hydrocarbons that we used in the making of roads. Okay, here is an exam question on the stuff that we've just talked about. It's just the beginning of one. Please pause the video, have a look, and then move on to the actual part of the question. Okay, so crude oil vapour passes up the column that was shown on the previous slide, and it asks you to complete this sentence. Please pause the video and attempt the question here. Okay, so we know that the crude oil enters the distillation column as a vapour, which means it's a gas. The vapours rise up the column and it gets cooler. Therefore, each fraction will condense at a different level. So the word that we wanted was condenses, and this is where it goes from a gas to a liquid as it gets cooler and reaches its boiling point. Remember, boiling points are the points at which something boils, and the same point where something condenses. Here's the next part of the question. Pause the video and decide which box you would tick. So the answer is that fractions have different boiling points. As discussed on the previous slide, the vapour will condense to a liquid when it reaches its boiling point. As the temperature changes as you go up the column, different vapours will condense at different levels, which are called fractions. So we separate fractions using their boiling points. Final part of the question, pause the video and decide which alkane is shown in this model. First of all, we need to remember that the black circles represent carbon atoms, whilst the white circles represent hydrogen atoms. Then we need to count the number of carbons present, which in this case is 3. This tells us that the diagram shows the alkane propane, which is the one that has 3 carbons. Okay, now we're going to talk about complete combustion. So we use the lighter fractions of crude oils as fuels, and when they burn in excess oxygen, hydrocarbons can transfer lots of energy to the surroundings, and the carbon and hydrogen atoms in the fuel are oxidised completely. So the products of complete combustion are water and carbon dioxide. Using the example of propane on the screen, we can see the word equation and the balance symbol equation for propane. Can you use this to help you write the word equation and the balance symbol equation for the complete combustion of ethane? Okay, so we would have ethane plus oxygen goes to carbon dioxide and water, and then I will let you check whether we have got it balanced. Okay, so here is an experiment that helps us to prove that both carbon dioxide and water are produced during the combustion of a crude oil fraction. So the ice bath here causes the condensation of the water vapour that is produced here when the natural gas is combusted. So here our blue cobalt chloride paper will turn pink if water is present. So the ice bath allows the water vapour to condense into liquid water, and then it will turn this paper pink. We can then bubble the remaining gas product through the lime water, which will allow us to test for carbon dioxide. If the test is positive, the lime water will go cloudy. The other type of combustion is incomplete combustion, and this occurs where there is insufficient oxygen getting to the fuel. And we can tell the difference because in complete combustion you'll have a very clean looking flame. It's often a blue colour. So if you've got a gas hob at home, or when we open the tap on your Bunsen burner in school, whereas if it's orange, that means it's incomplete combustion. In this process, less energy is transferred to the surroundings and carbon monoxide gas is formed, as well as carbon dioxide. Okay, so we can do this thing called cracking. It is a process that allows us to turn larger hydrocarbons that are in less demand into smaller, more useful hydrocarbons. So the larger fractions are heated to vaporization, and the vapours are then passed over a hot catalyst or mixed with steam and heated to a very high temperature, allowing us to form smaller hydrocarbons that are more useful to us. So here we can see that decane, which is a 10 carbon alkane, can be cracked when heated to 500 degrees with a catalyst. We can then form pentane, propene and ethene. So as you can see, cracking produces a mixture of molecules. Here, pentane is an alkane, meaning it only contains carbon-carbon single bonds. We can tell that by the ane at the end of the word. Whilst propene and ethene are both alkenes. Alkenes are hydrocarbons that contain a carbon-carbon double bond, and they are known as unsaturated molecules, and they are drawn down here. We can see the carbon-carbon double bond present. Here is a way that we would carry out cracking in a laboratory. The apparatus shows us the equipment we would use. Here we are cracking paraffin using heat and a catalyst of broken pot, and we are able to test the gaseous products that are formed. We can prove that the alkenes burn in air, that they don't burn as well as the small alkanes that do not contain the double bonds, and we can show that alkenes react with bromine water, which would turn from orange to colourless when that double carbon-carbon bond is present. And this shows that alkenes are much more reactive than alkanes. The test with bromine water is only positive with unsaturated hydrocarbons, so it is an easy way for us to determine whether we have an alkane or an alkene. Finally, here is an exam question on cracking worth 3 marks. Pause the video and attempt the question. In this question, we need to discuss why cracking is useful. So, a mark would be given for saying why cracking is useful, and it is useful for breaking larger molecules into smaller molecules. Another mark would be given that we do this to satisfy the demand for the smaller molecules, as they are more useful to us. For the final mark, we needed to give an example of a molecule that could be cracked. So, an example would be the cracking of residue, which makes up 48% of crude oil, but is only 38% of our overall demand, would allow us to produce more petrol, which makes up only 9% of the crude oil, but our demand for it is 23%. You could have picked other examples so long as the one you were suggesting to be cracked was larger than the one needed to be produced, and it had a higher percentage in the 3rd column than the 4th column. So another example would have been kerosene. this number here is larger than this one here. Whilst the product being made had to have a higher percentage in the fourth rather than the third. So an example would be gas. This is higher than this. Final part of the question. So this is another example. Pause the video and have a go at answering this for 2 marks. Okay, so with a describe the differences question, we need to be clear when comparing the differences between the two processes. For example, it is not enough to say that cracking involves a catalyst. We need to say that cracking involves a catalyst, but distillation does not. This makes it clear to the examiner that we know the difference between the two processes and don't just know about one of them. The second mark is gained for saying that cracking involves a chemical change, while distillation does not. I hope this video has been useful to you, and we will see you soon.